So today we're going to be looking at heat diffusion through some control volume in Cartesian coordinates, and we're going to be deriving an expression for the heat diffusion. So we're going to start off by looking at a control volume in the shape of a cube, where we have some amount of heat entering on, we'll just say this left face for the sake of simplicity, and it'll be exiting from this opposite face and traversing this distance dx. Let me try rewriting that. And since our goal is to derive an expression for the overall heat diffusion and how we can plug in things that may change the temperature within the control volume, such as a reaction or energy being stored or removed, heat being stored or removed, we can go ahead and just write an expression for qx plus dx and work from there. So we have qx plus dx, and since we have some amount of heat entering, that will also have to be removed, minus or plus whatever heat is being added inside this control volume. So in that case, we're going to say the difference in heat per unit length times the actual length of this segment dx. So we can really look at this as a sort of energy balance equation where we have some amount of energy coming in minus the energy coming out, and some amount of energy being generated within the system or being removed from the system is going to be the total energy within the system, stored within the system. And if we want to look at something like this, energy generated, we can define this variable, this rate variable, energy generation, meaning this is how much energy is being generated per unit time. And it's simply going to be the amount of heat we can generate per unit time times the total volume that heat is being generated in. Or, the heat generated per unit time and unit volume times the total volume that the heat is being generated in. So in this case, our Q dot, or our heat generation per unit time and unit volume, it looks something like this: joules per seconds meter cubed, something like that, times our differential volume, or the total volume of our cube, is going to be equal to the total energy generated for a given amount of time. In this case, our cube, the differential volume of our cube, our control system, can be expressed as simply the differentials of each of the dimensions of the cube, so the x, y, z directions. So instead of dv, we can just write this as the product of dx times dy times dz. So next we can come up with a term for this energy storage. And I actually changed this from energy system to energy storage just because it's a little more accurate. The total energy stored in a system might not be the energy in the system at any given time. But for this is also going to be a rate variable. So E dot is going to be equal to our density times our heat capacity at a given pressure times our difference in temperature with respect to time times our differential volume. And credit to Mike O'Connell for how he explained this, but something that helped me was just looking at the units. So we have kilograms per meters cubed. We have heat capacity, which is just, sorry, I'm getting Alexa notifications, joules over kilograms times Kelvin. So we can go ahead and cross these out. And then we have our change in temperature with respect to time. So we have kelvins over seconds, those cross out. And then we have our differential volume, which is our, it's just going to be meters cubed in this case. So we can go ahead and cross those out, and we're just left with joules per second if we're using SI units. And then this dv can also be rewritten as dx, dy, dz. So now when we plug these expressions into our original energy balance equation here, we'll have the energy in, which is just q sub x, minus the energy out, which is q sub x plus our differentials of q sub x over x times dx, and then our energy generation, which is q dot times dx, dy, dz, is going to be equal to our rho heat capacity times our change in temperature with respect to time, and times dx, dy, dz. And we can go ahead and just simplify this a bit. These q sub x's will cancel. This becomes a negative. And we're left with this expression here. And then from here, we need some sort of expression or formula for this q sub x to solve for the total equation. So we do have a formula for this qx term right here, which is just Fourier's law of thermal conduction, and it is expressed as qx is equal to the second differential of qx times the area, and this can be further broken down to a rate constant, well, really a negative rate constant because the heat is being conducted, it is leaving a point to go to another point, times the difference in temperature with respect to time, times the area of that face. And in this case, the face is dy times dz. So this is dz, and this is dy. So all we have to do is plug that in up here, and we're going to be left with negative k dt over dt dy dz, and then we can't forget the dx plus q dot dx dy dz is equal to rho cp dt over time dx dy dz. And sorry, I actually made two errors there. Instead of with respect to time, we're looking at with respect to position. And then I also did forget to rewrite the differential over the difference in position. So we can start canceling across. These negatives will cancel. We have dy, dx, dz in all three terms, so those will all cancel out. And then here, with these canceled, we're going to have the second derivative of temperature. With respect to position, plus q dot is going to be equal to our density times our heat capacity times our difference in temperature with respect to time. So from here, we can just do a little more simplification and substitution. So let's go ahead and divide across by k, which I did forget to write down previously. I added that here. So we have d squared t over dx squared plus q dot over k. Q dot over k, it's going to be equal to rho times our heat capacity times the change in temperature with respect to time over k. And now we can introduce something called alpha, which is just our... Oh gosh, I'm really bad at drawing alpha, so let me try this again. There we go. Is equal to our thermal diffusivity over our density times our heat capacity. And this just accounts for how the heat is going to diffuse through the material given its properties. So in this case, our final equation that we're going to be using in the next part of the series is second derivative of temperature with respect to position plus Q dot over K is going to be equal to 1 over alpha times the change in temperature with respect to time. And we're going to be using this to analyze a bar in the next problem that we're going to be... Here, let me... There we go. Now you can see it. We're going to be using this to analyze the heat diffusion through a bar. If we were looking at a three-dimensional shape and we cared about how it diffused in other directions, we could also include terms for the x and y directions, but in this case, we're only going to worry about the if we cared about the y and z directions, we could include terms for those. But in this case, we're just going to leave it in the x direction.